Hi there, IB. Welcome to the next chapter. In this section, we're looking at linear modelling. So it's another area of statistics and is probably a lot more real world because life's not quite simple like we looked at in chapter 20. In chapter 20, there were just basic measurements and we looked at frequency. In this section, we're looking at two variables. So not just one variable that's changing. Here we're going to have two variables. So this opening problem looks at an athlete. At a certain age, he can throw a discus a certain distance. And so the whole statistics around, well, how far can he throw? Doesn't age make a difference? If you're older, can you throw further? And all those questions come into it. So in this case, we'd get a whole lot of data and then do all those statistics on it, find mean and median and all those. We could also plot it up. So when we plot this sort of data, we're plotting it with age against distance. So here we have two variables. So that's different to the first chapter where we had one variable along here and this axis was our frequency. So we've got two variables, two things that are changing. If we think about as age goes up, we look at the data in the table and it's not done in order, so it's a little bit harder to see. But if we plotted that data, we can see here our youngest at 10 years through a distance of 15 metres and our eldest at 20 through 50 metres. And if we plot it, we might find our data looks something like this. So we'd have different values. And we generally find that as you get older, the distance that you can throw increases. So the question we might want to think about is it just a linear relationship, straight line, or maybe at a particular age you can throw the furthest and then after that you can't throw as far, so it might start going down. You may have another situation where at the beginning you can't really throw anything at all until a certain age, and then it goes up and then it plateaus, and then maybe when you're hitting your teenage years it suddenly goes up again. So we can have a whole lot of different types of relationships describing the two variables. In this topic we're looking at linear modelling, so we're going to be looking at things and how they relate to a straight line. So plotting our data, we can then come up with a straight line relationship. So this is what this one looked like. And we talk about those terms of dependent and independent variable. So our dependent variable is that, our independent variable is the one that we're controlling. So we're saying, let's choose particular ages. The dependent variable is dependent on what age we choose. So depending what age, then that determines how far we can throw. All right, so we usually have our independent variable on our x-axis and then our dependent variable on the y-axis. All right, so the dependent comes up on the y. In this case, our y-axis is distance in metres, our x-axis was age in years. Note this little notation here if you haven't seen before. That just means there's a gap in the axis. So if this is 0 here, but this is 10, that's not 10 units because here we've only got 2 units between those two lines. So it just means we've got a bit of a break in the axis and we've just squashed it together. Same story with the y-axis. So we're going to look at, to start with, this term correlation. So we may have used that just in everyday life to go, what's the correlation? What's the link between these two? So in mathematic language, correlation refers to the relationship or association between the two variables. And it's going to describe, we're going to have several words that describe that correlation or the relationship. The first one is direction. So here's some data like we looked at for our age and distance. Here's some other data that goes down. So this could be something like, let's stick with age, how old you are, and what would be some quantity that would decrease as you get older. Maybe the time to run 100 metres, that as you get older, you get faster. So time or 100 metres. All right, that may not be a straight line, but it's something that decreases. And in this one, we can see the data's all over the place. So there's no clear relationship. So we use the term a positive relationship for this one. And in that case, it's because it has a positive gradient. As x increases, then the y increases. So that's what we mean for a positive relationship. As that gets higher, the y value is increasing. Whereas in the next one, as x increases, the y goes downwards. So we'll go, let's go yellow. So as this one increases, we're finding the y decreases. So we give that a term negative correlation because it has a negative gradient. The line, that line of best fit, has a negative gradient. As x increases, y is decreasing. And this one has no correlation. There's no way we can draw any straight line through there for it to make sense. Another term we use to describe it is linearity. So here's two that have both a positive correlation. They're both positive. As x increases, positive, the y is increasing. But here, this makes a nice straight line, whereas this one's curved. And that curve should look familiar to you. Hopefully that reminds you of the log graph, or the log function. So that's a logarithmic relationship, whereas this is a linear relationship. So in other words, we could use something like a y equal to mx plus b to graph that, where here we'd be looking at some sort of, say a natural log, we'd have some numbers here, ln of x. We might do a plus b out here or something to model that. So both increasing, both positive, but different shapes. The next one we want to talk about is the strength of it. So here we've got, they're all positive correlations. In other words, as x increases, y increases. Both are linear, so if you look at those points, they roughly lie in a straight line, except for this one. But now, see how the density of the points close to the line is different. So here, the data points lie very closely to a straight line, and here they're just sort of vaguely around it. And in this case, they're all over the place, but still generally positive. So strong correlation means really close to the line, moderate and weak. So we can talk strong positive or strong negative. So here, the points are really close to the line, but it's a negative slope. In this case here, we've got moderate positive, okay, reasonably close to the line, but it's positive gradient. Here, negative gradient, reasonably close to the line. And in the last two, they're both weak, but you can see the difference between a positive and the negative. So the positive one, the points are roughly following that line, whereas down here the points are roughly following a negative slope. All right, so when you group it or draw a circle around it, not a circle, a line around it like that, it's a bit easier to see. So we've talked about direction, positive, negative, or no correlation. Linearity, is it lie close to a straight line or some other function? So it may not be. In this topic, we're mostly going to be looking at linear functions. And then the third one here is the strength. Is there a strong correlation, moderate, or weak? The next thing we want to talk about with data is outliers. So basically, you probably talked about outliers before, but if we've got some isolated point which doesn't conform to the trend of the main set of data, or the main body of data, then we call it an outlier. So it's still, it still fits on our, in this case, a negative correlation, which is reasonably strong, like they're quite close, But here we've got 2 points that are an outlier. So they're a long way from the other points. So in this case, it's a long way from the rest, but it follows the trend of the data. So we don't call it an outlier. All right? Whereas this point is a long way from the data, but it doesn't follow or doesn't conform to the trend of the data. So that one we do call an outlier. We want to think about causes of outliers. So there could be things like what's called a systematic error. So that means some built-in error in the instrument. So if for some reason there's something wrong with the instrument and we get a strange result, sometimes that could happen with all the data, but maybe it just turns up in one. The battery got low, started to run down at the end, and so the results were strange. So something to do with the instrument, that there's some problem with the system or the actual instrument. You might just have a random piece of data which is different. So if you had Usain Bolt running at the Redlands Athletics Carnival, he would be an outlier. His time for the 100 metres would be so much faster because he's just different to the rest of us, all right? The other causes of errors are sometimes just human error. We've written it down incorrectly. We just made a mistake. We forgot to put another zero in or put the wrong decimal place, so some human error. Or it could be someone is just lying. They're going, well, I said I read 100 books during my holidays. Well, maybe they did and they were a genuine outlier, or maybe they weren't just telling the truth. So different causes for outliers. The question is, when do you ignore them? When do you include your outlier? Do we include Usain Bolt in our Redlands data? No, because he's not a Redlands student, he's too old. And so when do you include them and when don't you? So the systematic errors, could be a built-in error. So that one, you're probably going to need to fix the problem with your instrument. Let's just go a different colour. So that one you're probably going to ignore. If it's just a random piece of data, which is just different, but it's a legitimate experiment and no problems with the instrument, then you're probably still going to include that. If there's human error or someone's lying, so if you just made a mistake, then you're probably not going to. So when you ignore them, you've got to think how valid they are. Is it a valid piece of data? How valid is the data? Oh, this writing's all over the place. So is the data valid, even though it's often not matching the same trend or not? So that takes a bit of a judgment call. Okay, the next section here is on causation. There's a lot of just talking with this, a lot of information that you haven't, some you would have come across and some not. Causation talks about, does the one relationship or one variable cause the other? Even though there is a strong relationship or strong correlation, does that mean there's causation? So first of all, you need to think about which is your independent and which is your dependent variable. So which one's causing what, in theory? So in this example here, the arm length and running speed of a sample of young children were measured, and a strong positive correlation was found to exist between the variables. So if it's a strong positive correlation, that means we've got data that's really close to a straight line. So I'm going to draw it vague, really close. Here's our straight line going to come in. Oh, let's even go with a line. That one, and we'll go get some colour happening. So, that didn't give me my line. Okay, nice straight red line. So that implies we've got a strong positive correlation because it's a positive slope and the data is really close to the line. Question, if you train more, you'll get faster. Will your arms grow? So that's a question. If this is our independent variable, the arm length, So in other words, we're saying that's the one we're measuring or controlling. So this is our arm length. So we go right for this arm length, and let's put a N in there as well. All right, what speed do we run at? So speed is our dependent variable. Just going to fix that. So, not likely. If you train more and you get faster, I don't think your arms are going to grow. If we got someone and stretched their arms, do you think they're going to run faster? No. All right. So, we need it writing. So, even though we do those things, we don't see we get an effect. It just happens to be a relationship. If you stop training for a year and so ran a slower time, would you find that your arms had shortened over that time? No. All right? So we can't say that the length of the arm causes the speed. What's the variable that comes into it? Yeah, you probably guess. It's probably something like age. Training comes into it, but it's certainly not your arm length. So as you get older, your arms get longer, and it just happens to be, therefore your speed is. So the correlation between two variables does not necessarily mean that one variable causes the other. If it does cause a change in the other variable, then there is a causal relationship. So if arm length did cause it, then we say that's a causal relationship. In this example in your textbook, we've got a mass hanging on a spring, and for different weights, so here's our weight in grams, we get a different length of the spring. So in this experiment, this is written on the top, and that's usually our independent variable. So we're controlling the masses at the end of the spring, and when they were measuring how far does the spring stretch. We get this sort of data, and then when we look at that data, what's it look like? So it looks like we've got a straight line, so it's looking quite linear. The direction is positive, so you could have stopped and filled these in. So as the mass gets heavier, the length of the spring gets longer. The strength, strong, medium, moderate or weak, I'd go strong because the data points are pretty close to a straight line. Do we have any outliers? Not in this case. There's no data that's sticking out. Causation. The question is, does the masses or the increased mass cause the extra length? Yes, there is causation. So that's a nice introduction to correlation. We then, in the next section, want to go, well, we've used words for these sort of descriptions. In maths, we like to be a bit more specific. Is there any way we can put some numbers to describe these rather than just words? So thanks for listening, and we look forward to seeing you in class. Bye for now.